Hi, I'm Alex, and my co-authors' names are Jason, Thomas, and Kent Larson, and we are going to present Urban Mobility Swarms, a Scalable implementation. We're presenting a system to coordinate what we call urban mobility swarms in order to promote the use and safety of lightweight and sustainable transit. Our design is inspired by nature, but it's built for a city environment. More abstractly, this is a decentralized peer-to-peer system where nodes communicate over radio messages and where coordination and synchrony is an emergent property. Our particular implementation is to synchronize light across bicycles. In this presentation, we'll cover the problem statement and design goals, and then what the swarming behavior and bicycle lights is, and then dive into the technical description and hardware before concluding. So Jason is going to talk about the problem statement and design goals.
In our research group, we think a lot about the future of cities, and research indicates that approximately 90% of population growth through the year 2050 will occur in cities, which has significant implications for global climate change. Energy-efficient mass transportation infrastructure is expensive and limited in coverage, but lightweight vehicles, such as bicycles, offer a low-cost, sustainable alternative. But there are limitations, and a limitation of particular concern to us is the perception of safety at night. So to address this question, we have developed a series of system goals in which there is a mechanism that reinforces membership in a community of users of lightweight mobility modes, that participation increases a sense of belonging for all users and increases safety, and requires minimal maintenance and management, such that it can be applied to many transit modes such as bicycles, skateboards, and scooters, and it just works. The solution we proposed was inspired by nature. We looked to nature, the insects of the night, for inspiration, and particularly looked at crickets and fireflies, who both show emergent properties of synchronization as they express themselves in close proximity in a swarm at night. The properties of the system we have proposed, which is inspired by nature, will intrinsically embody a series of properties that are essential for the deployment of alternative mobility modes, such as scalability, simplicity, and flexibility. To achieve the self-organizing swarming behavior of the system, we developed a software specification with the following properties. There is no global clock. Nodes communicate peer-to-peer via simple radio messages. Nodes need not be predetermined nor share metadata about their identities, and nodes can immediately synchronize when in proximity of each other.
Thomas is going to present swarm behavior and bicycle lights.
We implemented the swarm behavior and lights in our local shared bicycle vehicles in Boston. The lighting system can be embedded in bicycles and scooters and synchronized across riders. In the video, you can see when riders are alone, the lights are steadily on. When they come near each other, the lights begin to gently pulsate in synchrony with the other riders around them. This allows riders to collaboratively enhance their collective presence and safety on the road, while creating a visual presence of the rider community. When riders are riding in the street, depending on the distance they're riding, the lights synchronize around them if the rider's around.
I'm going to dive into the technical description. So we model our bicycles as a decentralized network where nodes are a part of a swarm when they are near each other and in synchrony. Nodes have two states. They can be out of sync when their lights are steadily on, or they can be in sync when their lights are oscillating. And what we show in figure 2 is the two states where two nodes are initially out of sync because they're further away from each other. One catches up to the other, and then they are in proximity and can exchange messages and enter a state of synchrony. Then when they go away from each other, they exit that state of synchrony and go back into the out of sync mode. You could have multiple swarms in the larger network. These different swarms can merge and become larger swarms, or all of the nodes might be separate from each other and just all stay out of sync. Or you might have small swarms that are further away from each other in a larger network of swarms. In order to implement this, we use the fact that synchrony has a transitive property, and we use peer-to-peer messages broadcast over short range and a synchronization algorithm. In terms of how we use the property that synchrony is transitive, when two nodes are in sync, another node that comes near them only needs to synchronize with one of those two nodes in order to be in synchrony with the others as well. Our system allows multiple swarms to merge as well as separate. We model nodes as oscillators. So again, they have two states. When the nodes are in synchrony, they have a phase value that oscillates between 0 and a fixed period, which we'll call t. When they're out of synchrony, their phase value stays steady at 0. When nodes are in sync, it's because their phase values align. We then use light as a function of phase, where the amplitude of the light oscillates with the phase. So when the light is steadily on, it's because the nodes are out of sync and their phase stays at 0. Then as the phase begins to oscillate when they become in sync, their light amplitude oscillates with that phase as well. In order to synchronize nodes, we have a message broadcasting and synchronization protocol. Each node broadcasts its phase as a message and receives the phase messages from other nodes around it. Each node updates its own phase value to match the highest value, whether that's a message that it received from another node or its own phase value. This allows nodes to synchronize. A design requirement for our system is that nodes can be anonymous and that our system can be flexible in terms of allowing any new node to enter the network without having a predefined identifier or address. The way we address this requirement is to have n predetermined addresses, and each node chooses a random number between 1 and n and uses the address corresponding to that number and listens on all other addresses. So it broadcasts on its chosen number address and listens on all other addresses. To handle collisions, which will happen every once in a while, out of sync nodes periodically update their node numbers to handle the chance of collisions. And for synchronized nodes, collisions will be okay because the messages that are broadcast around them are redundant. Our system achieves our privacy goals by allowing nodes to be anonymous. One security issue we want to address is that faulty and malicious nodes could hurt the synchrony of the nodes around them, but these attacks will be spatially isolated. Thomas is now going to discuss the hardware.
We implemented the software on the hardware and a custom board PCB. We also fabricated and designed the enclosure and the fabric that straps around the bicycle. The components of the circuit has 18 mega, 8-bit, which we use Arduino. It has a radio module at 2.4 gigahertz that transmits and broadcasts the information to the other nodes. And this can be tuned depending on the distance. We also designed the enclosure for the box, which all the circuit goes inside the box and straps around the bicycle at the Mia Lab. And we use as well 12-volt battery for the LEDs and also for the power supply.
So in conclusion, we presented urban mobility swarms, which were inspired by nature, but that we implemented as a lighting system for bicycles in order to promote the use of lightweight and sustainable transit. This can go beyond bicycles. That can be used for scooters and more in order to improve the sustainability of cities going forward. And the reason we are presenting to you in this virtual format is due to the health pandemic of COVID-19. And going forward, we have to recognize that bicycles and scooters might be more desired options because they keep people at a naturally safe distance, while other sustainable shared transit options like buses and trains might be considered more dangerous. So we hope that this can help improve the sustainability of cities going forward, as well as the safety of riders, and improve the privacy as well of the individuals that use the system. Thank you.